All right, gonna go over a couple things for class. First thing we're gonna start with are pressure volume loops, okay? So, pressure volume loops. Kind of like drawing this out with a graph here, like this. Okay, we're gonna put this at 10, and this at 120, and this is measured in millimeters of mercury. Okay, and this would be our pressure measured within that unit, and then this is going to be our volume. And what we're doing is we're talking about the ventricle. Okay, and then so we got our volume. So then we'll have I believe it's like 10, and then we'll have 120 milliliters, and that's going to be measured in milliliters. Okay, and so one thing that I want to do is also label, that this is 50 milliliters here. Okay, so the way I think about these is, you have some set point here, and we fill up to 120 milliliters, and that'll put us probably right here at the 10, right? In terms of pressure, 10 millimeters of mercury. So we're at 120 milliliters here. At this point, something unique happens. So this whole spot here represents the atrium doing systolic contraction, which is 20 to 30% of filling up the atrium. But before that, we have, atrium passively fills the ventricle. And we know that that's 70, 80%. Okay. And so right here, this is called, right here, two things are happening. Right here, the AV valve, also known as if we're talking about the right atrium or the left atrium, we're talking about the bicuspid valve. This AV valve shuts because the pressure in the ventricle has exceeded the pressure in the atrium, like we talked about with the cardiac cycle. So then our pressure shoots straight up, and this is called the isocentric contraction. Okay, and our pressure shoots way up, and then our volume decreases, and then we come back down here. So right here, our pressure is going to shoot straight up. So when this shuts, that's where we get the sound lub. Then this one, our semi-aortic semilunar valve will open. Okay, and when that opens, we lose a ton of volume of blood, because not all of it, but a lot of it, because it's getting pushed out of the ventricle. And so this spot here we call our preload. And this stuff up here we would call our afterload. Okay, so we have our preload, and then we have our afterload up top. So that aortic semilunar valve will actually open up, we lose blood, and slowly start to lose that pressure. And then the pressure in the aorta will exceed the pressure in the ventricle and will shut the door, so we don't lose any more. And we shut that door, so aortic semilunar valve shuts, okay, and that's called dub. Okay, so aortic semilunar valve will shut, and that's dub. And then we have this decrease in pressure that will occur. So we lose volume, and then once we lose enough volume, our pressure will start to go down. Then once it shuts, our pressure will drop all the way back down, and then we'll open up here. This is where the AV valve opens. Okay, let me make sure I got everything. So yeah, AV valve opens there. And then on this side, this would be our isovolumetric relaxation. Because here we have systolic ventricle. Ventricle. Okay. Perfect. All right, so we got all that going on. Now, what do we want to understand here? Well, right here, when there's no change in the volume, but we have this change in pressure, we call this the end diastolic volume. And this is the end systolic volume. Okay, so end diastolic, end systolic volume. Okay, so what do we get from that? Well, we get something called stroke volume there. And if we make a couple equations over here, we know that stroke volume equals EdV minus ESV. Okay, and that's going to tell us that where the valve's shut and where the aortic semilunar valve shuts, stroke volume will tell us the amount of blood that's going to be leaving, right? Yeah. Stroke volume is going to be the volume of blood pumped out with each stroke. And so it's not always 100% because it's not always going to contract 100%, okay? So we have this equation. We also want to know another equation, and that is that cardiac output equals heart rate times stroke volume, okay? And this is important for us to know because we have an example here with obese people. Okay? And I'm going to take a stab at this, trying to explain this without looking at my notes. But from what I remember me writing down is with obese people, they have a decrease in stroke volume. Okay? And so you have to increase stroke volume, and then you do that by increasing heart rate. And that's because their preload is down. And because their preload is down, it shortens here, so it shortens the stroke volume. So in order to increase stroke volume, you have to increase something. We increase heart rate, okay? So then this makes the heart work harder. And that leads to an increase in myocardium. So over time, you decrease the space of your ventricle, and permanently for time, decrease the preload, which then will continue to have high heart rate and high blood pressure. Okay? Yes, let me make sure I got all this right here. So yeah, so basically everything I said is you're like right here. And so you have low EDV, which equals low stroke volume, which equals high heart rate. And that's why obese people have high heart rates and blood pressure. Okay, inotropy. So basically we have something here called an inotropic line. So if we were to label our dot here and we could label this all the way up to here, this would be our inotropic line right there, okay? And basically what that tells us is the amount of contraction that we're doing up until that point. So we're doing this much contraction of the heart to get that blood out, because we know that this part, the afterload, is taking place because of the ventricle squeezing, twisting to get that blood pumped out through the aorta. And so what ends up happening is we increase, so inotropy, increase in calcium, which increases in muscle contraction. Okay. And I think that's all I kind of wanted to put on there. Elastance. So we can increase our elastance, but sometimes, you know, you can change preload or afterload here, and let's just say our afterload changed to here, right? So then watch this. Now my inotropy will change, and we need more inotropy, more contraction. And so this is also something called elastance. Increases, and that's stiffness. So the stiffness of the atrium will increase with this elastance. So we just call that greater contraction. So this elastance increase, so we have greater contraction, which also means greater volume of blood leaving ventricle. If elastance is high and inotropy is increased. Okay? Coolio. So, this is also going to be labeled our change in pressure over change in volume as well. We kind of want to know that. And then we have another word that we use there. Okay? So, preload. So I'll demonstrate preload really quick here. So it's going to be preload. Okay? So some things that we need to know is same thing. We have our 10 and we have our 120 up here for pressure. If we started here and we raise up to get here and then we come over to here, when we talk about preload, we're talking about this area here filling that ventricle. And so we can sometimes increase preload and we can continue going on like this, and then we come up and then we come over, and this would be an increase in preload. And what preload is our venous return. Okay, venous return. And so we know that those are coming through the inferior and superior vena cava, and those will dump into the right atrium. And what ends up happening is preload can be affected. So in this case, if we're increasing preload, then we're increasing that venous return. So we could be exercising, right? There's a couple other things that we can do. We could be lifting our legs. And all this increases EDV, end diastolic volume. This part here that I labeled up here, it's increasing that. So if we increase EDV, we increase that venous return, and then we have an increase in preload. But preload does not mean that we increase afterload, and it doesn't mean that we move our inotropy. But it does mean that stroke volume has increased. Okay? And I'll label this as stroke volume. And that continues over. Now with exercise, we're contracting the muscles, and we know that venous return works through the return of that blood through the contraction of muscles. And so we also have, we have that going on, but then we also have dilation going on of those blood vessels. And so we get an increase in venous return occurring, which I think can be a good thing. But EDV changes without ESV changing. Okay, perfect. So we have some treatments that we can do for preload. Well, not preload, but afterload. And let me do that one in blue. Remember, afterload is going to be that contracting of the ventricle and how hard it needs to contract in order to allow us to pump that blood from the ventricle, from that left ventricle into the aorta. And so if we were to continue with our diagram here, we had 120 up here, and this was right here, and we went like this to here, and we came up and over and around, and this was our 120 right here. Right? This section here is going to be our afterload. And what ends up happening is sometimes we can change that afterload here, and we can cause more pressure to be needed. But I'm pretty sure it often changes, how much. So the pressure goes up, but we often change how much volume is actually pushed out because we need an increase in contraction. So afterload often plays a role on increasing inotropy. So the same things in the cardiac cycle that affect the dichrotic notch, those are going to be the same things that affect the afterload. And so it has to do with that pressure in the ventricle. So sometimes inotropy can remain constant. And when it does, we get this, where our stroke volume has decreased significantly. So in order to get that stroke volume back up, we have to increase inotropy and increase the heart rate, because we know that stroke volume equals heart rate times cardiac output. So if stroke volume went down and we are trying to maintain that same cardiac output, then we're going to need to increase the heart rate. And we do that by increasing inotropy. which increases calcium, which increases sarcomere contraction and the neuromuscular junction. Okay. And this allows EVS to decrease, so we can maintain that length. So a couple of key things to think about is if we were able to increase the inotropy here, then it would look like this, and we would continue down like that. And we would maintain our same stroke volume. But we do know that we're tied to needing an increase in inotropy, calcium, sarcomere contraction of the myosin, what is that system called? It's called like a muscle cardiac cycle. No. Anyways, myosin head will contract. So cool. So some things that we're doing is we're increasing resistance. Which increases pressure during the ejection phase. So some ways that we increase afterload. So if I put down some examples of how we increase afterload, it has to do with the aorta. So we could increase viscosity of blood. Okay, we could increase stenosis of the vessels, meaning narrowing. We could increase vasoconstriction. Okay, that's one way that we can do this. We can increase vasoconstriction. Or we can narrow the valves of the semilunar valve. So smaller semilunar valve, or we can do vasoconstriction. Okay, and those are ways that we affect afterload and why we need more pressure to push the blood out, and that pressure to continue to exceed long enough past that pressure, and contraction to be strong enough to exceed that pressure. So then we can have this work the way that needs to, having our stroke volume to be the same. So then we maintain right here, same cardiac output. Okay, perfect. Well, I think I got most of this stuff for here. One way that we can treat afterload is, instead of having to worry about increasing pressure and all that, we can treat it by increasing inotropy, like I showed you here. We can increase preload, so venous return. We can increase exercise. We can increase elevation of legs. Okay, so these are some simple things that we can do to change that. Increase alpha 1 antagonist, because we know alpha 1 does vasoconstriction, so this would increase that, and we would do vasodilation, right? And so these are ways that we would treat afterload. Okay. So the last thing I want to put on here is a drug. I'm pretty sure it's a drug, but it's called digoxin. And I kind of want to explain how this can work on the cells, or on this process of actually increasing or decreasing the afterload and having an effect on contraction with the muscle. So digoxin, how it works is you have that action potential propagating down. Right here you have a calcium channel, and then you have your sarcoplasmic reticulum. So the endoplasmic reticulum of a cardiovascular muscle cell, so it's sarcoplasm. Right here, calcium binds, and this is an RYR channel, and then we would release calcium from inside. Okay, we know that calcium, that's a calcium-induced calcium release channel, but we know it reuptakes can occur of calcium, and that's going to be through the circopump. But we also have this extracellular calcium that's coming into here that needs to come back to the ECF, extracellular space, extracellular fluid, intracellular fluid. So this calcium needs to get back out, and it uses this type of transport, active transport, and we're going to send in 3 sodium, and we send out 1 calcium. And this is called the H, or the NC channel, NCX channel. Exchanger. Okay, so what we notice that happens with this is digoxin blocks or inhibits this NCX channel. And it does this in a way that allows the calcium that's supposed to leave to stay in the cell longer, and then it can go to the cross-bridge cycle. And we can allow that calcium to stay within the cell longer and do the contraction that it would do with myosin, with removing tropomyosin out of the way, binding to troponin C, moving tropomyosin out of the way, allowing troponin C, or troponin, allowing the G-active site of the actin to be open, allowing the myosin head to bind to it, and then to complete the cross-bridge cycle. Okay, so that's everything there. Okay, now we're going to get into blood pressures. This one's a little bit more tricky in kind of understanding how this works, but we'll get through it. Okay. So the first thing I want to draw out is this graph here. And these are going to be pressures, okay? And what I'm trying to illustrate here is there's a difference in the amount of pressure that different types of arteries will take. So these are going to be the aorta. That's going to be the aorta. That will be the aorta. This will be large arteries, arterioles, veins, capillaries. Pretty sure that's how that works. Oof. Mix these two up. More particular venules, which are little veins. Okay, so you can see that there's this change in pressure that these different vessels can withstand. And so aortas, they have the highest pressure within them. Large arteries have a good amount. Arterioles are the smallest of the arteries. Capillaries, it's a capillary bed. We'll talk about that in the next section here. And then veins and venules, which are going to be that venous return back to the heart. Venules are going to be our smallest ones, though, the smallest type of veins that we encounter. Okay. So we kind of know already what all of these do. Obviously, the arteries are going to be taking blood from the heart to the tissues of the body. The capillaries are where that actually exchange will happen, where we drop off O2, which we took from the lungs, right? And then it's going to also drop off any nutrients and then pick up anything that it needs to. So there's an exchange that occurs at that capillary bed, and then we have the veins, which will do the venous return, and venules will kind of come out of those capillaries, and then they'll form into the inferior and superior vena cava, and they'll dump into that right atrium, and then we'll allow for blood flow to continue through the cardiac cycle. And so something that we want to understand is this term called MAP, which stands for mean arterial pressure. Okay, and this is important to understand when we talk about blood pressure. Okay, so this is also blood pressure, mean arterial pressure, and it equals the cardiac output times the peripheral resistance. Now we know that cardiac output actually equals heart rate times stroke volume. And then we know that stroke volume equals EDV minus ESV. And diastolic and systolic volumes, right? And we know we can change heart rate in order to accommodate for changing stroke volume to have that same cardiac output. Now PR, there's an equation that we would write for this one. And then when we change heart rate, you know, one thing we do want to mention is there's two ways we can do that. We can actually increase heart rate, and that's through the sympathetic nervous system. And that's alpha 1 receptors with norepinephrine. And that's beta 1. Indirectly, alpha 1 can cause it by vasoconstriction, and then we have a decrease in heart rate. We went over this last time. That's PNS, and that's muscarinic 2 receptors, acetylcholine. Okay? That's how we control our heart rate. So it's kind of good to see kind of how these equations relate to concepts and to understand them conceptually. For peripheral resistance, we have peripheral resistance equals 8VL over R pi R to the 4th, okay? So we know length plays a role, and we know the radius, the distance, also plays a role in some things that we want to understand. And so we know a couple things. Distance affects like resistance, viscosity of the volume. But the most important one is radius. And that's that distance that it's going. The radius of the returning vesicles, right? So of arteries, you know, they can be controlled by alpha-1 receptors. So alpha-1 will do vasoconstriction, and if it's not doing, then we do vasodilation. And these affect radius, okay? Right, so if we take the radius here, that's the diameter, but the radius would be half this, right? And so that thickness, if it vasoconstricts, where the radius will go down. If it vasodilates, then the radius goes up. And so we see that these things play a role on this part of the equation here, and we'll kind of talk about how that works, okay? So there's two ways of changing R. We can do either one, vasoconstriction or vasodilation. Okay? And so what ends up happening is if we do vasoconstriction, then our radius will go down. If our radius goes down, then our PR, peripheral resistance, will go up because it will be a bigger number, which means our blood flow will increase, will decrease, which means our stroke volume will decrease, which means we'll have to correct it by increasing our heart rate. So this is the SNS response, as I pointed out over there. So we have alpha-1, which will do vasoconstriction. Okay, I don't think I'm doing that one. I'm doing more of the changing of the heart rate. So increased heart rate will be beta 1, and decreased heart rate will be M2. Well, I'm not doing that one here. And then norepinephrine is our neurotransmitter. This will increase heart rate because we'll do this one will be alpha-1, and then we'll do vasodilation. Vasoconstriction. Okay. And then we're able to do some vasoconstriction and have that going on there. There's two drugs that we use for this. If we want to increase vasoconstriction, we can do vasopressin, or we can do angiotensin. Okay? Vasodilation. So in vasodilation, we're going to increase, not resistance, but increase radius. Peripheral resistance will decrease. Which means our blood flow will increase, and our stroke volume will increase. So we'll decrease our heart rate. And we decrease our heart rate through the PNS response, parasympathetic nervous system. And how this works is we're going to use acetylcholine on an M2 receptor, and this causes a decrease in heart rate. Actually, I don't think that that's all right, because vasodilation isn't controlled by that. But the heart rate does go down, so we have epinephrine on a beta 2. On a beta 2 receptor. And I guess this releases some molecules here. So we'll decrease O2, increase potassium, increase hydrogen, and increase CO2. Oh, decrease CO2. And so histamine, adenosine, and bradykinin, histidine, these are nitric acid. These are things that we would use, nitric oxide, to facilitate in vasodilation. Okay? Now, let's talk about baroreceptors. Let's talk about baroreceptors. I'm pretty sure these are controlled by the adrenal medulla. Okay? So let's talk about baroreceptors. Baroreceptors are going to be pretty cool. Because with baroreceptors, what we're doing is we're looking at the heart and how it's going to respond to stretch. So you have your heart like this. And this is going to be our left ventricle. And this is where the aorta comes out of. And then we have that three-dimensional aorta here, aorta. Up here we have several valves, arteries that split off. And these all have these stretch receptors within them. Okay, and these are innervated by the central nervous system, and they're going to come off here and allow something to happen being tied to the adrenal medulla. Yeah, this is called a corroded sinus. Okay. And basically something that we need to understand about this is the PNS and SNS, right? And how they innervate and how they work with this. And so what ends up happening is you have the PNS and the ANS, parasympathetic nervous system, autonomic nervous system, okay? And PNS will innervate through M2 receptors. And they use a neurotransmitter called acetylcholine. And they decrease heart rate. Rest and digest. Autonomic nervous system, increase heart rate using beta 1 receptors. And they use norepinephrine as their neurotransmitter of choice. Okay, so we have this vasoconstriction that can occur as well on here. Which will lead to increased heart rate because it affects the afterload. So I kind of want to think about, all right, how does oxygen affect us? Well, oxygen will affect this by, if you increase O2, you're holding more blood, so that will decrease your blood flow, right? Okay, so if you increase O2, you're going to increase heart rate, because preload low. So then you're going to increase vasoconstriction. Which affects afterload as well. If you decrease O2, then you decrease heart rate and increase vasodilation. Okay? So those are baroreceptors. Stretch responsive is kind of how I think about them. Okay, now we have the chemoreflexor or receptor reflex. I'm gonna erase some of this here. Okay, chemoreceptor reflex. Boom. So the chemoreceptor reflex is basically you have low O2, low oxygen. And if you have low oxygen, then you have high CO2. And if you have high CO2, then we're going to increase in these protons that are within the system. And so this is called stimulating the chemoreceptor response. So if CO2 increases, then we know that that's because blood flow increased. Especially like coming through venous return, right? So if there's less oxygen, that means there's less blood in the lungs and more blood to be pumped. Okay? An example of this is called CNS ischemia, or lack of blood flow going to the brain. So a decrease in blood flow to the brain, and what this does is it increases heart rate and increases vasoconstriction. Vasoconstriction. Which increases blood pressure. And this can lead to death if it's not treated. This is your body's kind of like last chance to try to stay alive. Something that we also need to know is called long-term regulation. And how this works is called PAAS, stands for, or RAAS, and stands for renin, angiotensin, aldosterone system. Renin, angiotensin, aldosterone system. So the first thing that happens is the kidney releases renin. The second thing that happens is renin converts. Angiotensin to Ang1. And it goes to the lungs. And then ACE converts Ang1 to Ang2. That Ang2 can do some cool things, okay? Which we will explain right now. So, it can increase vasodilation, vasoconstriction. And this will increase heart rate. It also reduces ADH. Well, this actually increases peripheral resistance, and so MAP goes up because we know MAP equals peripheral resistance times cardiac output. Okay, aldosterone. So H2 is going to reabsorb, so then this will lead to low urine, high thirst. Okay, we increase aldosterone. So that means that sodium is reabsorbed. And potassium leaves out of the kidney. So these two together, we have low urine, secretions, prevents decrease in blood volume, prevents decrease in blood pressure. Okay? So this is kind of how our body can regulate blood pressure and keep things in a homeostatic place, with homeostasis. Okay? Okay, last thing we're going to talk about is capillary exchange. Okay? So we have capillary exchange. Taking place, right? Something that we want to understand about capillary exchange is you're going from an artery to a vein. And I like to change up the colors a little bit because it kind of helps us visualize what's going on. So this is capillary exchange. This is the venous side. And this is the artery side. Okay? We know that the pressure on this side is higher. And this one has a lower pressure on this side. Okay? So we also know that we have these muscles here, okay? This is called a precapillary sphincter. And what's important about this precapillary sphincter is it's a smooth muscle. Okay? And so dilation equals, I believe, the contraction. Dilation of this would equal relaxation of the precapillary sphincter. Okay? There's some molecules that can do that and cause that dilation that kind of secrete from a nearby cell. And so we would have CO2, we would have potassium, hydrogen, and sodium. Okay? Well, no sodium, but we increase everything. This one's O2. But we would decrease that, we would have an increase in these ions, and that would cause the relaxation of the precapillary sphincter, thus leading to a dilation of that precapillary sphincter, allowing more blood flow to come in. So it's regulated. And so these local mediators determine which tissues, which capillaries get blood. Okay, perfect. So within this, we have a couple important features. We have HP, which on this side it's high. Then we have a pressure, and that's coming out. We have a pressure coming in called BCOP. We have a pressure coming out, again, called ICOP. And then we have this lymphatic vessel here. Which comes and sucks up excess fluid, called ICF. IFP. Okay. And this right here is called our interstitial space. And these lymphatic vessels have these things called valves on them. And they work like a vacuum. Okay. So, one way that these things work is BCOP works by, solutes. And if they're permeable, we don't count them. But albumin's big enough that it doesn't permeate or leak through the membrane on most occasions. And so albumin will stay in there, and that actually increases the BCOP with allowing those fluids to come within the cell. Okay? So there's a little chart I want to draw up here. So we have so up here we have forces, we have arteries, we have veins, we have out, in, and we kind of want to label what their pressure is coming in or out. So up here, we have ICOP, we have BCOP, IPF, IFP, HP, and total. We're going to use that across the whole board here. So, what ends up happening with this is we have some numbers here. So HP, or blood pressure, BP, is going to be 30 going out. IFP is about 3 going out. BCOP is about 28 going in, and ICOP is about 7 or 8. About 8 going out on the arterial side. So we have a total in of, I believe, like 13 or 13 out. It is the total there. For our net. Now on the other side, IFP stays at 3 coming out, ICOP stays at 8 coming out, I believe HP will drop to about 7 to 10. So it goes down to about 10, and then this will stay at 28 for our B cop, but that'll be in. And so we have a total of 7 in for the fluids. And that's how we can get this side to release its liquids and nutrients and oxygen, and this side to take it in and go. And so those fluids will enter capillary bed. And these will exit capillary bed. Okay. So now I kind of want to go over an idea of how edema works. So let's talk about right-sided edema. The right side of your heart goes out. So what kind of edema would that cause? Well, if we think about it, if the right side of your heart, the right ventricle and atrium weren't working in your heart, let's just say the right ventricle, right? Well, that means that you're not able to get blood back through the superior and inferior vena cava. And so what that means is you have blood pooling that kind of just stays towards your legs. And so you get swollen feet and you get edema that occurs in the cells because that fluid will come back to here and it will come back into the interstitial space here. Right? And so then we get this swelling in that interstitial space. We have left-sided heart fails. So if the left-sided heart fails, your venous return is normal, but you're kind of backed up, right? So your venous return is normal, your stroke volume is going to be low. And stroke volume is low because I believe you probably need a little bit more afterload. So it's going to change some things. So this increases blood pressure, and the venous side of the capillaries will have edema. Now, a sprained ankle, you're gonna break the cells within that area, and so they secrete they secrete the things that they have inside them, the solutes. And when those get secreted out, they're actually going to float in the interstitial space and suck water out of them through osmolarity. And that's going to come out and mess with this whole system. And so you would get swelling because fluid's coming out. And so you would have swelling as well, or edema. And there's many other ways, but that's a good amount to start with. So thanks.